continuing along here and picking up with this section on the uncertainty principle, which is a really famous part of quantum mechanics. You're probably familiar with Heisenberg, the Heisenberg uncertainty principle. And so we're going to build up that discussion using these generic examples, okay? But as we progress through the course, we will see actual physical implications of the uncertainty principle, okay? So I'm first going to start with our generic wave function, psi equals ae ikx plus be minus ikx. And I'll remind you, we got this wave function from solving the one-dimensional time-independent Schrodinger equation. So it's kind of accurate, but not completely, because it's only one dimension, right? And so also recall when we were talking about operators, we played this game of operating on psi with the momentum operator. And we played this game by saying, well, let's call b equals 0 and see what the result is. And then let's call a equals 0 and see what the result is. And so I'll remind you, when we said b is equal to 0 and the momentum operator operates on the wave function, we get back the original wave function plus the eigenvalue. And so that eigenvalue very much represents the momentum of the particle. And so recall k is that wave number solution. So it's like the 2me divided by h bar all square root, all right? So, but we'll just represent that as a constant for now, okay? And so also recall when a is equal to 0, we got this negative k times h bar, okay? And so there's a couple consequences of this, all right? And so if we now start thinking of this momentum state as a property of particles, okay? So in other words, I've got a particle flying through. It has mass and it has velocity, therefore it has momentum. We want to know now, how does that particle property translate to a wave property, okay? So I can think of that now as some total wave function being psi plus and psi minus related to each of these two terms, okay? And in the case for psi plus, we could view that so as a particle with momentum positive kh bar, and that means in this 1D scale, this would be a particle traveling in this direction, okay? And so recall that also came from our discussion of the second derivative giving us this idea of curvature and kinetic energy. So as you can see here, the kinetic energy is very low, and it picks up and it picks up and it picks up, and it really increases going up this curve, okay? Well, we also have this negative momentum state given by negative kh bar, okay? And we could view that as a particle moving to the left in our 1D Cartesian coordinate scheme, okay? And so what we have going on here now is, what this implies, the physical implication of this is, in a large number of measurements, there will be an equal probability of finding particles moving to the left with this negative kh bar momentum state, and particles moving to the right with this positive kh bar momentum state, okay? And so then the idea, what we would see is we'd find the most probable value to be somewhere right there, okay? So what we call this, when we see this very sharp wave function giving us a peak, we call that a wave packet. And that's this idea of this confluence of wave properties and particle properties converging to this singular point of where we might find the particle. It's the wave packet, okay? So another amplification of this is a wave function is a superposition of more than one wave function. So in this simple example, we might see this as a superposition of two wave functions, one describing a particle moving to the right, one describing a particle moving to the left. Okay? And as we build up more and more of those wave functions, like it says up here, we would find an equal probability of particles moving left, particles moving right, owing to this being the most probable position. Okay? Let me erase that terrible looking arrow. Okay. So what we need is a linear combination of wave functions. And by linear combination, we just mean psi plus, plus psi minus, et cetera, et cetera. And we call this the basis set. And this basis set will describe a particle's physical properties with as much accuracy and precision as possible. And really, precision here is the key, because the more narrow that peak gets, the more precise we get. Okay?